we use something called regularization techniques, also called as penalized regression algorithms. Now, basically, regression models suffer from two things. The first one is bias. Regression models generally suffer from two important problems. One of the problem is bias. What is bias? Bias are the underlying assumptions needs to be independent or dependent for reducing the cost function. Now, bias are underlying assumptions that need to be met for the model to perform well. Multiple linear regression, binary logistic regression, they have a lot of assumptions. What is the assumption in multiple linear regression? The most important assumption is the dependent variable must be close to normal distribution. On independent variables, the most important is no multicollinearity. If these two are not met, then your model tends to fail. So biases are the underlying assumptions that are need to be met for the model to perform. Now, also, the reason why bias is there is bias helps in reducing the complexity of model. Bias help in reducing the complexity of model. Training time means model building time. Easy to identify. High bias leads to underfitting problem. What is underfitting problem? Not reaching the 0.60, less than 0.60. For you to accept a multiple linear regression model, the R square should be in the range of 0.60 to 0.95. If it is less than 0.60, it becomes an underfitting model. That means the model has not performed well. There is some problem in your data. We see it in some data sets, right? Where our R square was less than 0. Predominantly when you have large amount of skewness in dependent variable. When your dependent variable is highly skewed, your model will definitely underfit. So what we try to do, we do logarithmic transformation. But logarithmic transformation works. See, as long as the skewness is 5 or less than 5, logarithmic transformation works. If it is a larger value, like skewness is 10, 20 or 30, no matter what transformation you do, it will not work. So transformations also has a limitation. If the skewness is smaller, closer to 0, then we can do something. But if the skewness is a very large value, say 30 or 40, something like that, no matter what transformation you do, it will not work. So that is what underfitting leads to. Similarly, low bias, overfitting, too good to be true. R square greater than 0.95, this we call it as overfitting. So underfitting is also a problem, overfitting is also a problem. Too good to be true. We have to leave some sort of variance for other variables. We don't know what happens. So see, in businesses, we never thought COVID 3 to 2 years, now COVID has become, or pandemic has become an important variable in demand forecasting. In demand forecasting, prior to COVID, we had pandemics like SARS, swine flus, bird flu, all those things are there. But they never caused a disruption such a big enough that the whole economy went into recession. Prior to 80s, we had these pandemics because of droughts, famines, cholera, tuberculosis. We had those famines. That time our economy was closed, nobody knew it. Now, what is happening is globalized economy, pandemics happen, everything collapses. Your supply chains collapse, your productions collapse, your demand collapses, your business people will go into losses. So there is a huge disruption in the economy. Now COVID has become a variable. So you need to have some variance left out for unknown variables. There will be something which will come up, unknown variables. These unknown variables can be pandemics, natural disasters. Unknown variables can be changes in government policies. Suddenly there is a change in government policy. Now Government of India says by 2040, they want to have only CNG and electric cars on roads in India. What will happen to the combustion engines of petrol, diesel, guys? Shifting from one business to other business is not easy, right? That will be very difficult. It is happening in two-wheelers, electric two-wheelers. Lot of people, everybody, I know hundreds of startups only building two-wheelers electric. But big guys are not building any, big people are not building any two-wheelers because there are still a lot of risk involved in electric two-wheelers. They're the batteries are bursting, they are burning, fire catching, all those things are happening. So there is no battery which is prove what you call sound enough temperature of India. Because if you have a battery, it has to be kept under 40 degrees, between 30 to 40 degrees. Our climate goes to 40 to 50. Imagine summer coming and people using electric bikes, the batteries will blast. That is what Bajaj says, Rahul Bajaj says. There is still problem with batteries in electric. So they stopped it. He wanted to launch Chetak as an electric car. Tata's want to launch Nano as electric car. But the battery is still a problem. Charging is still a problem. People putting in homes and to charging, and they're creating a lot of problems. So there will be some unknown variables always. So we have to leave certain amount of variance for those variables. That is why a range has been defined, right? So this is the context of bias, which is one of the problems in what we call regression. High bias algorithms, multiple linear regression, binary or logistic regression, both binary as well as. Now, the second problem is variance. Variance is a type of error that occurs due to the model's small changes, fluctuations. Variance is an error that is caused by small changes. You build a model and you give a new data, and that data has small changes in the data, the error will become large. That we call it as variance. Variance is one of the problem in regression, where when you build a model, it looks very good. When you give new data to the model, the variance will, particularly if the new data has skewness, kurtosis, outliers, or any minor fluctuations, there will be significant changes in, okay. So variance is high variance caused by noise in data, outliers. Another thing is high variance overfitting problem. High variance causes overfitting drastically. Prediction scores drastically changes. Cross validation, right? Cross validation shows us that, there will be drastic change. So high variance will cause that. High variance algorithms, non-parametric algorithms. So parametric algorithms, bias, non-parametric algorithms, variance. Okay. So bias and variance, they are very, very important concepts you need to understand when you are looking at. So both of them will cause in regression. In regression, particularly in regression only, this will cause a lot of. So this diagram will help us to understand. If you have this is called underfitting. Good fit means all of them in the lane. And if it's zigzagged, it is overfitting. High score, low score, again high score, low score. Underfitting means you have either all towards one side or either on to the right side if you draw a straight line. So underfitting happens when there is high bias and low variance. When there is low bias and high variance, so you need to find something here. What we call, this is the area where we want to go between, where both of them will be at a lower point, where we want both of them to be at, then it will be a good fit. Bias variance trade-off is very, very important. If you are confused with that diagram, you can see here. This diagram should give you the bias variance trade-off. And there is always an irreducible error. Irreducible error means we don't know. Irreducible errors means what will affect the data. Somehow the model doesn't fit. Despite doing all sorts of things, still the model doesn't fit. That we call it, we have something called irreducible error. Irreducible error can be, real data will always have skewness and outliers. Can we eliminate them? No, we can only minimize them. See, in machine learning and data science, error cannot be zero. Error cannot be zero. Error will only be minimized to an acceptable level. When you are saying minimizing, that means there is a difference between zero and that minimum level, right? That we call it as irreducible error. This is zero. You are drawing an error curve up to here. This is your minimum possible error, which you are accepting. That means this difference is called as irreducible error. Now, irreducible error can be caused by anything. Because we have variables other than what we have in our data. Other than our data, there will be some other variables which we might have missed them, or we are not considering them. So there will be always some irreducible error in your model, which you cannot eliminate. Irreducible error will be always there. It cannot be eliminated. So basically, we can't we can't make zero, anything zero in machine learning. Zero is not possible. We just need to minimize it to an acceptable level. Minimizing means to upright. Even in the gradient descent, we had that thing, the curve will not touch the zero, right? It is above the zero line. So same thing here. So this is your underfitting zone. You can see here bias, and this is your variance, and you try to find somewhere which is acceptable to you in between. This area will be the point where you will try to accept the model. So this model fitting complexity is very, very important. That's what we try to balance, right? When you are looking at models, when I'm telling you which models you have to go in sequence, means to understand the bias and complex variance. That's why I always say start from the basic model, go step by step to understand this context of what is causing the variance, how much variance it is doing, which model is where. That's where you will be able to understand a better understanding of the data as well as the model which you are going to finally implement. See, we always don't target 90% accuracy or R square 90. Sometimes you have to accept 70 to 80 with the values between 70 to 80 also, because of this problem of bias. And that's what we do now. We reduce the depth of the tree, whereby the score will, and then as it reduces, the cross validation also will come near to it, and then we accept a level score which is fitting on a repeated test model. So bias and variance has to be balanced. So in real-time data science, we generally prefer scores between 70 to 85. Frankly speaking, we will be happy with those models. Competitions and all, that's a different scenario where you target 99, 95, all those scenarios. But in real-time data science, getting a 70 to 85% itself is a good fit model. Your cross validations, your bias and variance all will be in a range. My personal experience, above 85%, closer to 90% and all, you will have the problem of bias. And so we generally prefer that range of models. So when we work on real-time data, we get that right. On the, we generally get overfitting on decision tree, which we control by the depth. Once we control by the depth, the score goes to 80, right? We accept that model because that is a better fit model compared to a overfitting. So you always look for that range. Not that your model should always have 90. No, 80 to 90, you are lucky. But most of the times it will be 70 to 85. So that is what you have to accept. And that is where this whole bias and variance, overfitting, underfitting will come into picture. So we need to have a good fit model so that we can use it repeatedly on multiple times. Variance is sigma x minus mean whole square divided by n minus 1, which is a univariate statistic. Covariance is bivariate statistics. That means you have two values, x minus mean multiplied by y minus mean, y minus y mean divided by n minus 1. That is your covariance, sigma. Sigma x minus x mean multiplied by y minus y mean divided by n minus 1 is your covariance. That's a bivariate statistics. Variance is a univariate statistic. Overfitting is one of the common problems which we see in data. To control overfitting, one method is reduce model complexity, reduce the model variable selection or feature engineering, reduce model complexity by reducing the variables or by scaling or standard, something we try to do to reduce it. If you don't want to do it, the second most preferred method is regularization. The second method is regularization. Is a regression technique estimated coefficients of the model to either. So regularization is one of the popular method which is used that basically shrinks or reduces the size of the coefficients. You know betas, right? The betas are the one which we derive from the regression equation. Beta 1, beta 2, apart from the intercept. It doesn't touch the intercept. It only plays on the coefficients, the betas. How it does is regularization minimizes the validation loss, adding a penalty. Typically, we use for penalty called, we use the word lambda to the coefficients. So thereby it will shrink the values. A penalty means what? A negative term. Penalizing means what? Shrinking or reducing. You got 100. Penalty lambda will reduce it to 90, or it will reduce it to penalizing means reduction from the original value, or shrinking from the original value. We call it as appreciation is different. That is increasing. Penalizing is reducing. That will do. I'll tell you. Now, within regularization techniques, we have multiple algorithms. The first one is and selection. Full form of Lasso is least absolute shrinkage and selection, also referred as L1, also referred to as L1 penalty. So Lasso sum square error lambda absolute values of where lambda is equal to 0. If lambda is equal to 0, multiple linear regression. If you don't give any value to lambda, it is simply a multiple linear regression model. So the lambda value must be greater than you can give a very large number also. Okay. But if lambda is very large number, all the coefficients will be shrink to 0. So if all the coefficients will become 0, there is no point, right? So you have to find a value for lambda which will give you the best fit model. Again, there is no fixed model, fixed formula for doing it. Generally, we give lambda values as 0.10, 0.20, like that. You give multiple lambda values, build a model, and find the best possible lambda value. That is the only method of finding the lambda value. Now, Lasso is a variable feature selection method. As some of the coefficients in the model by default, Lasso will make some coefficients 0, particularly which are smaller to coefficient which are already closer to 0. It will make them. Once the coefficient becomes 0, it is no point. The variable will be eliminated. So Lasso is a variable or feature selection method. Like we have decision tree-based models where we get feature importance. Similarly, Lasso also performs similarly, but it's in a different manner. Their importance is taken. Here, some of the coefficients will be made 0, thereby eliminating some variables in your model. Variable reduction technique. Lasso is a variable reduction technique. If you give n variables, you will get n minus variables as output, because by default it will make some variables. So Lasso is also used as a variable selection method. The disadvantage is Lasso does not work well with multi-collinear data. With multi-collinear data, Lasso does not perform well. So Lasso is a very important regularization technique which is used to reduce the variables by making some coefficients, by adding a penalty to the sum square error or the object. It doesn't look at that part. It just looks at the variables as numbers. See, none of the machine learning algorithm understand the variable name. No machine learning algorithm understands the variables. It just plays on the numbers. No machine learning algorithm or statistical or anything looks at the variable. It doesn't discriminate based on gender or something like that. It is just a place on the numbers. Only numbers are it doesn't look at the data as names or headers or anything. It just looks at the what interpretation that we have to make out of those output of numbers. But algorithm does not take into consideration. Headers are not important. Variable types are important. Numerical, categorical, those are important, but names are not. They only focus on numbers. So it doesn't know which is important variable, which is not an important variable. After calculation, feature importance is generated based on the Gini or the entropy in trees. Here, based on the coefficients which are non-zero. That we have to interpret. It will not. The second type is ridge. Regression, also called as, ridge to the power of 2. The magnitude coefficients. In the top, it is absolute value of the coefficients. Here it is absolute value of coefficient. Here it is squared value of coefficient. Here coefficients are squared. In Lasso, we will take the absolute value. We will ignore the mathematical. Here we square the coefficients. Of course, both do the same thing. If you square it, negative will also become. If you take absolute, you are ignoring the negative sign. You will treat it as same. Okay. So only difference is it takes the absolute value of coefficients. Here it will take the squared value of coefficient. So here also lambda must be greater than 0. Here also lambda must be greater than, else it becomes multiple linear regression, normal multiple linear regression. So you have to give a lambda value greater the lambda value or shrink, coefficients will become closer to 0, but not In Lasso, coefficients will become 0. They will become closer to 0, but never. It only reduces the size of the coefficients to a smaller value, but it does not make the coefficients 0. So ridge cannot be used as a variable selection. Ridge regression reduces the coefficient size towards 0, but does not make it. Hence, it cannot be used as a variable selection technique. It cannot be variable, or so it will tend to bring to 0, but not. Ridge reduces the complexity of model. Ridge reduces the complexity of the model. Multi-collinear data. It works well with multi-collinear. Elastic net, which is combination of Lasso plus, it is a combination of Lasso plus Ridge. When Lasso has a bias, a particular set of variables. Sometimes what happens is in Lasso, some variables are given too much of importance and other variables are given lesser importance. Elastic net helps us to bring all the variables to a balanced. So elastic net is a combination of both Lasso and Ridge. So here we have to give two penalties. Two penalty terms have to be assigned. One penalty term for Lasso, one penalty term for Ridge. Two penalty to be assigned, one for Lasso, one each for Lasso and Ridge. So first Ridge is implemented and then Lasso is implemented. So this is also a variable selection technique. First Ridge regression is implemented, then Lasso will be implemented. So elastic net is also a variable selection technique because Lasso is also there, right? So elastic net is also a variable or feature selection technique. Okay. So the three methods which are used in regularization are these. Let me see if I can get a table for your comparison. I think there is no comparison table, not available. So if you look at the what we have in Python, so sklearn.linear_model is Lasso. So here the penalty is called as alpha. They use the word alpha, which is nothing but the lambda, which is used in the theoretical part. This is the alpha. See here, alpha into absolute value of weights. L1 prior as regards aka the Lasso. The optimization objective is Lasso is square root of n into n samples into absolute y minus xy plus alpha into this value. Now alpha default is 1. Alpha default is 1 because if you give alpha as 0, it becomes a multiple linear regression model. If alpha is 0, it becomes a multiple linear regression model. So alpha must be default greater than 0. So it has to be 1, and you can give alpha value till infinity, but it should not be negative. Alpha value must be positive. It can be given, but I told you now very large alphas will shrink all the coefficients to 0. So that one you need to understand. So in Python, we call it as alpha. So the alpha values, you can give multiple value, and accordingly, you can use grid search algorithm to find the best possible alpha. Similarly, ridge. Here also alpha. Again, 0 to infinity. Okay. So lambda or alpha are same. In sklearn, they use the word alpha. So that is the value which we need to give. Elastic net. So combination of both alpha, Lasso and Ridge. Combined L1 and L2 priors are regularizers. This is L1. This is what you call L1, L2 separately must be greater than. Copied the cells. What happened? Yeah, paste cells. Everything got pasted into one place. Huh? So hit escape to enter command mode. Control V to paste. So I have selected till where, Control C. So shift and down cells till the point where we have separated data till X and Y, na? Kegel house price prediction. Copy those cells to the new notebook. Shift and down arrow. Select those cells, Control C. Go to the new notebook. Select a cell, press escape and Control V. First press escape, then you will go to command mode and then Control V. Paste all the cells and run all. Copy it till the point where we did the linear regression model. Kegel house price prediction. Copy the cells till the point where we were about to build the linear regression model. Shift and down arrow. Shift and down arrow. Select the cells. Control C. Okay. Go to the new notebook or wherever you are writing the notes of bias and variance. Select a cell. First press escape and then Control V. It will paste. Otherwise, it will paste everything in one cell. If you press escape and Control V, it will paste cell wise and run all the cells. Run all the cells. No. Yeah, no shift escape, only escape. First select the cell where you want to paste, press escape and control V. So this trick you always remember, because when you work in real-time data science, you have to copy paste cells from different notebooks and build a lasso model. So from sklearn dot linear underscore model, lasso is equal to lasso model is equal to x comma convergence warning. You might want to increase the number of iterations. Max underscore iter is equal to 2000. Acha, increasing regularization is also another option it is giving. So max iterations 5000, comma alpha is equal to 10, alpha is equal to 10, it converges. Convergence warning means all the coefficients were not calculated. Remember this. Convergence warning means all the coefficients in the model are not. One of the most used option is increase the iterations. Second, for some models has to be done. In case of regularization, it is asking to increase the penalty. So I increase the penalty from 1 to, now let us take the score, 85.44. So what was our regression score? We got the same score. Okay. But marginal difference is there, but same score we got. So we reduce it to 5. Again, convergence warning is coming. 20. It's reducing, right? If I go to 50, so it has to be somewhere between 20 and 50. 8543. So this one, let us see the feature importance. PD dot data frame, open bracket, x dot columns, comma, np dot round, lasso, model dot coefficients dot sort underscore index. See, you can see zeros. Second floor BSF 0, half bath 0, BSF NSF 0, any other variable 0. So it made 3 variables 0. See, absolute 0. Only 3 it made absolute. We have done lasso build ridge also. Any parameters you have to give for ridge? So PD dot data frame, x dot columns, comma, np dot round, model dot coefficients dot sort underscore index. So none of the coefficients are 0. None of the coefficients are 0. So this is the process of ridge. From sklearn dot linear underscore model import enet is equal to elastic net. Enet model is equal to enet dot fit x comma y. Enet model dot score x comma y. You can predict on the test data set and try submissions on test data set in Kaggle. Okay. Can we move forward? So in classification, the most important problem is imbalanced data. Imbalanced data is where there is in the levels or classes independent. For example, has 51,000 observations and attrition, yes, has 4,800. So there is a huge imbalance in the data. Imbalanced data, accuracy will be good, and F1 score of minority class. So this is majority, this is your minority. Majority class metrics will also be majority class will be. So when you are looking at imbalanced data, we should not only go by accuracy, we should also look for precision, recall, and F1 score of the minority class particularly. Minority class is the smaller class. Now, in imbalanced data, one option is collect more data, but this is often difficult. The second method is undersampling, oversampling. Undersampling and oversampling. I will discuss what it is just now. And the third option is data using algorithm. You can create artificial data within the range of the data using, let us focus on the undersampling and oversampling. Undersampling and over, this is one of the most randomized sampling is done. Randomized sampling is done. Now, to understand this concept, just look at this graph. In undersampling, we pull all the rare events while pulling a sample of the abundant events in order to equalize the data set. So undersampling is executed on the majority class. Undersampling is where randomly observations from majority class deleted both classes deletion from the majority class. This strategy, when there is, you will implement this strategy when there is large amount of. Similarly, oversampling. What is oversampling? Randomly selected observations, minority class are duplicated multiple times, copy paste the rows equal. That is called oversampling. Randomized oversampling is implemented when you don't have large amount data, we implement, right? So you have undersampling, you also have oversampling. Randomize, simply increase and decrease that process, we call it as random undersampling and random oversampling, so that we can have equality of both the classes. Undersampling is done on majority class, oversampling is done on minority class. All right, can continue. Now, if you want to use algorithm based thing, then we have something called SMOT, minority oversampling. SMOT is a very popular algorithm which is used in balancing the. So this is how SMOT will do. Here, the green samples are the synthetic samples which are created, artificial samples which are created, the nearest neighbors algorithm. So it will take the closest neighbors and it will take the values of the close neighbors, weighted values, and it created. So taking these two close neighbors, it calculated this value. Taking this and this, it calculated this value. Taking this neighbors and this neighbors, it calculated this. So SMOT is an algorithm that is used to calculate synthetic data. Synthetic data means artificial data, data that does not exist. Okay, artificial data will be created, but the data will be within the range. Data will be within the range. Take for example, I will show you a simple calculation example. SMOT uses KNN methodology, K nearest neighbors methodology with Euclidean distance, and creates synthetic or artificial data which lies within the range. It uses random generator to generate the weights. So a weight also will be generated. So SMOT uses KNN methodology, K nearest neighbors methodology, to identify the nearest neighbors, what you call artificial data within that range. It does not create outliers. It does not create outliers. So the process, let us say I have an example. Two independent variables are there. Let us say I have these two data points. X1 is age, X2 is income. X1 is age, X2 is income. Okay, so I want to create synthetic data for these two variables. So what it will do is, it will choose a random weight between 0 and 1. Let us say it's randomly selected 0.60. It chooses a random weight between 0 and 1. It chooses 0.60 as the thing. Then it identifies the closest observations. So for income, it found out the closest observations as 3,500 and 2,800. 2,800 and 3,500 it found to be closer to one another. Okay, so 2,800 plus 0.60 into difference of 3,500 minus 2,800, it created a new observation called 3,220. It found out these two are neighbors, right? 2,800 and 3,500 are neighbors, right? Based on the value, they are neighbors. So it took a random weight 0.60, lowest value 2,800 plus 0.6 of difference of 3,500 minus 2,800. You got 3,220 as the new observation. 3,220 is in the range because the maximum value is 4,100. Similarly, for age also, it calculated a new variable taking 34 and 46 as nearest neighbors. So taking 34 and 46 as nearest neighbors, it calculated a new value called 41.20 rounded off to 41. So this in this method, it will calculate artificial data, synthetic data, and this data will be within the range. It will not create outliers. It will create within the data range itself. So SMOT works like this using this methodology. Randomly it choose. Yes, randomly selected anything between 0 and 1. It is purely randomly. So it's a random selection.
So if you run that again,
That's why you have to fix the cell. Now you have to choose a value first, random value first. It has to be fixed. You have to fix the value. Otherwise, it will create problem. Plain smooth works only on numeric data only. Smooth, the plain version works only on numeric data. In Python, we have smooth NC, which works both on numerical data and categorical data. Smooth N is only for categorical. There are three variants of smooth in Python. Plain smooth works only on numeric data. Smooth NC works both on numeric and categorical data. And smooth N will work only on categorical data. New versions of smooth are developed. Borderline smooth, SVM based smooth, support vector based smooth. A lot of smooth is being developed. So a lot of research is going on for creating, balancing the data. It's one of the area of interest in machine learning, which is being researched. So new variations are being developed. Now, based on the utility, based on your data, you have to choose one. But these are the ones which are available in Python. Smooth, Smooth NC, and Smooth N. The three variants are available within Python sklearn. Not sklearn, sorry, Imbalanced. You have to install a library called Imbalanced. Pip install Imbalanced. Pip install Imbalanced. This is not part of sklearn. This is part of Imbalanced. Imbalanced, imbalance learning. Borderline, lot of variants are there. So there's this smooth variants is there. So we have this one, borderline smooth, smooth ENN. ENN is the different types of nearest neighbors. Smooth ENN is what is it? No, we can use for both. So these are the variants that are available. Rose is also there. Rose is available in Python, R. Randomized oversampling technique. Rose is very good in R. I think it's implemented in Python also now. So you can see these are the different variants of smooth are there. Gaussian smooth, K-means smooth. Instead of KNN, it uses K-means algorithm. Then what we call near miss, stomach links. All these are for classification data. No? Imbalance is only for classification. Base mode. See, this borderline smooths and all, they will work on any type of data. Categorical what? We will use most frequent, right? So here only they have shown three models: adaptive synthetic sampling, hybridization smooth with stomach links. So it uses K-means. Clustering is used in categorical data. For interpolation, it uses K-means. So in categorical data, it either uses, it can use nearest neighbors also, because we will encode it, right? See, K-means also creates clusters, right? We didn't discuss it, but K-means also is like creating borders only. So it created cluster 1, cluster 2, 3, and then it calculates the ratios, and then finally it will give you the minority point for the ratios. So clustering is used in categorical data. I will explain it once we do the clustering calculation. So what we will do is HR analytics is there, na? Copy the cells from HR analytics into this file. That's an imbalanced data, right? We have this vaccine prediction, na? Flu vaccine prediction is there. H1N1 is imbalanced, right? So you can open the file. Before building the models where we have done the splitting, till that point you do it. All right, let me run it. So if you look at our H1N1 vaccine, there is a huge imbalance. H1N1 is the imbalanced data. So let us run all the models: oversampler, smooth, borderline smooth, and Imbalanced oversampling. Import random oversampler, import smooth, borderline smooth, SVM smooth, and K-means smooth. I think this is all categorical data, right? We implemented it on work data. I think we have to use smooth N, because all our variables are categorical, right? So smooth N will be used. So random oversampling. I have done random oversampling. Here, random overslap, random state. We are fixing the random state. Otherwise, every time it will change. The rows will change. By setting up the random state 42, you will get a fixed result even if you run it multiple times. The output will not change. Otherwise, every time the random selections will change. Because random number generator, every time you click, it changes, right? To stop it from doing that, you fix a random state. Random state, give any value. 1, 2, 3, 4, 2 or something. You give it, it will fix the random value. So you can see here, the original is 21,033. 5674 is the minority class. Now we got both the classes as 21,033 and 21,033. Fit underscore resample. We do fit underscore transform, right? It is fit underscore resample. Smooth N. Smooth underscore OS. Smart n, change the name there. So copy this. This would be y underscore majority class, minority class equated to majority class, but the rows will be different. Okay. So let us say y underscore random dot paid x underscore smooth. So there will be marginal differences. You can find it if you go variable by variable or row by row. You can check it. Okay. Then borderline smooth x comma vaccine labels H1N1 vaccine. Now you can try building the models on this data. Okay, look at this article, handling imbalance. In Google you can type, or I'll send the link by email. So from sklearn dot linear model import logistic regression. Logit is equal to logistic regression. Logit model is equal to logit dot x comma y max underscore iter is equal to 2000 is equal to logit model dot import classification report also. Classification report y comma logit. Oh, sorry, I'm using wrong data. Vaccine labels dot H1N1 vaccine. Now you can see, right? Recall is very bad, right? Logit over sample is equal to logistic regression. Logit over sample model is equal to logit over sample dot fit underscore random comma y underscore random. My iterations again. Over sample predict is equal to logit over sample model dot predict classification report vaccine labels dot H1N1 vaccine comma logit over sample predict. See, recall has increased, but precision and F1 score are bad. Precision and F1 score are not good. Recall has increased. Overall accuracy also 0.77, right? It was less than 0.83. Normal logistic model 0.83, but here it is less, right? But recall has increased, but still precision F1 score are. So logit n is equal to logistic regression mag, keep it like this, smoten model is equal to logit smoten dot fit x underscore smooth comma y underscore smooth. Again, iterations problem. Logit smooth and model predict smooth and predict is equal to logit smooth and model dot predict x underscore smooth. I think I have used wrong variable here. Yeah. It is not x, it is x underscore random. So what is the problem we got here? On input variables. How come it is 42066? So this has to be y underscore random here. Y underscore random. Because you use x underscore random and y underscore random, right? Now all the metrics are good. I was using wrong thing there. So we have built the oversampling. This is your oversampling model where we have used x and y random. Overall accuracy is 76. All metrics are looking good. Similarly, we have used here smooth classification report y underscore smooth logic smooth and predict. So increased 81, and all the metrics are looking. Accuracy also increased. Overall performance of the model also increased. So like this, you try the other models also, the smooth border, SVM, and K-means, and you understand the recall and F1s, how they have metrics have. So that way you can understand the impact of the various type of methods. Okay. So in this case, because we are getting the accuracy here, so I'm not printing the score. Otherwise, this is nothing but score, right? Accuracy. You can check the accuracy of the base model. Base model without sampling or sampling, we got very bad performance metrics. But accuracy was very good. Majority class, but once we done the simple random oversampling, accuracy fell down to 76, but all the metrics are closer. Once we done the smooth, the accuracy increased to 81%, and all the metrics are very, very close to one another. The predictive accuracy is now stable, right? So this is how the imbalanced data problem can be tackled. Imbalanced data is one of the, it will happen. Imbalanced data will happen in real-time classification problem. Because if you look at credit card fraud, will all people do fraud? No, very, very small number of people will do fraud, in the sense they don't pay. So 10 to 15%, that's all. max to max 20%. 80% of the people will pay the credit card bill or some minimum amount due or something. 20% will completely default. In loans, it is lesser. Loans slightly lesser, somewhere around 10 to 12% will be the default. 88% of the people will pay it on time. So you will always have an imbalance. Even in promotions, companies' promotions, only 10% of the organization's employees will be promoted, not all. Even less than 10%. 90% people will get general hike. Next level promotion happens in only 10% of the 15%, 16% is the attrition or 20% max. 80% people will stay with the company. So classification will have imbalance problem. You can deal the imbalance problem betterly with SMOT. SMOT is the preferred algorithm. It has been used in banking, finance, insurance, retail, all these places SMOT is used. Otherwise, your model performance will be bad. Now, it keeps on predicting wrong. Your confusion matrix will be very worst. People who didn't take vaccine are being reported as taken vaccine, which is wrong, right? Right here, no, this is 0 is negative, 1 is positive. 0 is negative, 1 is positive. So this will be true negative. This will be true positive. So this will be false positive here. No, false negative. These are the predicted values, no? False negative. So 3,400 false negatives is being predicted. That means it is predicting that 3,400 people have taken vaccine, but it is wrong, right? Now, if I do a cross tabulation of this, PD dot cross tab y underscore random, comma, over sample predict. Now we have 5629. 5629 is a large, looks like a large number, but the sample size also increased. Sample size also increased, right? So what is the false negative rate here? What was the total sample size? So 3,400 divided by total sample size of 26,707, right? 0.12.78%. Here 5629, the sample size of 42066. 5629, 42066. Here also it is predicting bad because logistic regression, no? So still it is predicting bad only. But maybe if you are looking at decision tree model and other models, it will be the false negatives will come down. Because this is the base model which you are building, which has a higher false negative rate. Making the predictions more accurate, because the predictions will be very bad if you don't do it. It will give you very worst predictions if you don't balance the data. 0 means people not taken. 1 means taken. 1 means he has taken a vaccine. 0 means not a taken vaccine. So 0 is negative, 1 is positive. Only one. SMOT would be better. See, there are many methods, I told you, no? The others are all academic methods. We have a lot of things, but we don't do all those things in business. We go with the basic ones, SMOT-N and SMOT-NC, that's all. More accuracy and better performance. So the other things will also give you better, but implementing them will be problematic because you can't explain them to the client. How? Because you have to explain k-means algorithm, then you have to explain k-nearest neighbors algorithm, then you have to do all those things. So understanding for the clients will be very difficult. They are academic models. See, I told you this is one of the most researched area. You can see the research papers also which are there. Once you go to that SMOT variants library, each research paper is connected to that one that is developed. So most of the models are academic in nature, right? So what Python guys did was SMOT, SMOT-N and SMOT-NC are the preferable ones, which they have included in Imbalance. Near miss and Tomic links are also there, which are undersampling techniques, but we prefer oversampling than undersampling. So when you have lakhs of data, then you can do undersampling. Suppose you have 10 lakh rows of data, 20 lakh rows of data. There you have to anyway reduce the sample size because you can't experiment on that much of data because your system will not work. So you have to randomly undersample. So there we randomly undersample to a smaller size and then we will use it for building or understanding the data. And when it goes to production, we'll implement it on large scale data on pipelines. But you can't experiment on large scale data because systems won't support, right? Your laptop won't support. 2 lakhs only, it is taking a lot of time. 2 lakhs, 5 lakhs also takes a lot of time. So, and statistics says you should be, a sample size should be somewhere around 20,000 or 30,000. Like I told you, na? 50 observations per variable, minimum 20 for regression, like that. You have to build a sample like that. Sampling and distribution has to be done like that. And then we do. Actually, in statistics, there are methods of different sampling also. Sampling, how to decide the sample power size also. There is a statistical way of deciding how much sample you require. And further, there is also test also, whether the sample size is enough for that size of data or not. So all these things are there. I'll take a session on how to do the statistical sampling size prediction and all. We will do that. Maybe next session or the other session we will do it. Or during R. R is better there because those tests are not available in Python. They are available in R. So we will do that time R. How to define a sample size statistically, sample and power sizing using probability and randomized things. We do that. R is open source, purely open source.